Welcome everyone to this new episode of the Xuglers in Climate Founder series. Today my guest is Jacob Roberts. He is co-founder of AlkaLi Labs. Thank you so much for making the time. Jacob is a former software engineer turned bioengineer, not a small change. And you're converted from bytes to atoms and a big believer that biology can tackle the world's toughest climate challenges. He's finishing his PhD in bioengineering at UC Berkeley and is applying synthetic biology to produce the next generation of renewable fuels. Jacob, you're now the co-founder and CTO of AlkaLi Labs, and your co-founder Luis is also here. Thank you for that. And the company is genetically engineering yeast to recover critical minerals such as lithium and cobalt from industrial waste. You're on a mission to power the EV revolution without drilling new holes in the ground. A very beautiful and broad mission. So first of all, welcome.
Hi, Fira. Nice to be here. Luis and I founded AlkaLi about 2 years ago. We are engineering yeast and other microbes to pull valuable critical minerals, especially those that are needed for EVs, out of industrial wastes. And we see one such waste on the left. This is acid mine drainage. So there's all this sort of nasty water that can come out of mines, like in Appalachia. You have all this runoff from like copper mines that is actually super abundant in sometimes cobalt and often rare earth elements. So these waste streams that in this case don't look improperly handled, but can actually be a huge supply for this cleaner revolution of our like industry. Another resource is pictured in the top middle. So Luis and I are on an oil field in Louisiana here, and we're standing in front of a tank that's holding wastewater from oil and gas production. And this is a small field by most standards. This tank is small compared to most operations. But it contains lithium. So a lot of oil and gas waste streams contain huge amounts of lithium. And we estimate that there's enough lithium in oil and gas waste, like is pictured here, to supply domestic demand for the next 10 years. So there's this really amazing way that this old industry that we're hoping to get away from oil and gas in the future can, as it trails off, can supply our minerals for the next decades. And the way we're doing it, there's two pictures in the bottom where we have, on the left, we have microbes. Microbes are these little vessels that we can dunk into the brine, and we've genetically engineered them. We've got a protein shown at the right that's been engineered so that they selectively suck up lithium. And the way we use these microbes in a process, like on the resources shown, is we grow them in a tank. You see there's a diagram on the right. We have a biomass tank where we grow the microbes. We then dunk them. We mix them with this mineral-rich brine where they absorb all the lithium or other critical mineral that they've been engineered to extract. We separate the microbes from the brine. We dispose of the brine as previously. Put them in water where they release the lithium. And then recycle those microbes. So this microbe biomass becomes this biosorbent that we can use to pull minerals out of brine, akin to other direct lithium extraction approaches.
So we have usually in this call a lot of people who are founders or interested in getting into the space. You used to be a software engineer at Project Loon at Google, and you made that transition. Now you're finishing a PhD. Can you tell us a bit more about what was the journey like, and how did you upskill yourself? It's such a different field.
I loved working at Google, and I think Google and X and Loon really are working on some unbelievably important problems. And yet I was like, I'd really love to find a job that I can work at where I feel like the pie is growing for everybody involved. That's sort of what drove me into biology first. I was like, there's all these spaces where advancing the science, and I think a lot of people on this call probably feel the same way. There's so much important work to be done that just helps everybody. Like these climate issues are really scary. So that's what there's a little push and a little pull. Biology is an amazing solution to some really important problems. And right, so I didn't go straight to climate. I was really just passionate about the substrate of biology. So I joined a transitionary lab. I didn't go straight to the PhD. I got a pretty good paying job at a hospital system working on cancer biology. Highly recommend this type of intermediate transition. I was able to be a software engineer, which is what I knew and had been trained at, and also I'm sure everyone on the call recognizes the Google pedigree. It was super helpful in getting that ideal transitionary position. So I was able to be a software engineer and then work with clinicians and bio PhDs and learn directly from them this sort of specialized skill set that wound up A, letting me get into grad school, and B, confirmed that, yeah, this is actually the thing I want to commit 5 years of my life to getting a PhD in. So yeah, I had a transitionary job, I think, is sort of the answer, in a fun field, but one that was very much aligned with the skills I already had.
You must have made the best of the water cooler to learn so much from people around you in such a specific field. I also wanted to ask about the team. Obviously, Luis is here with us today, but how did you two meet and decided to work together? How do you complement each other?
Yeah, we did a couple projects in grad school, and throughout that, he was sort of he was sort of founder shaped, idea guy. He had these we'd have happy hours where every week he'd be like, I'm stressed about climate, and I thought, what if we could do this? And that's proven to be a very useful attribute. Great scientist too, in a way that really complemented my background, because I was sort of a little amateurish, a little clumsy in the lab. But I think the thing that really was the attribute of Luis that really made me think this is someone I want to start a company with was he's like one of the most thoughtful, I didn't know he'd be on the call, one of the most thoughtful people I know. I was like, this is someone who when I'm afraid of how the company is going to be going, when we get rejection after rejection, I think this is someone that when I get angry, because I'm a person who gets emotional sometimes like everybody else, I feel like this is someone I can keep working with. Yeah, I feel like we can go through hell together, and we have.
That's a great point. I think we haven't talked that much about emotional aspect in this series, so thank you for bringing it up. I want to talk about the industry landscape. You touched a little bit about that, and our little icebreaker was interesting to see what people think. But I was looking at numbers from the International Energy Agency, and their projection, big strokes, right, is from 2020 to 2040, they expect cobalt demand to increase from 6x to 21x, and lithium to increase from 13x to 42x. So any of these numbers are already very, very big. I've noticed also in the industry, we have now different types of technology to harvest or to mine lithium, from mining with AI. We heard about cobalt metals quite a bit. Deep sea mining initiative, different direct lithium extraction, which I think you belong to, and then also option of recycling. So for people who are not expert, including myself, would love for you to give us a little bit of an overview of the different solutions, and why did you land on biomining from all the potential options?
Yeah, I want to sit with those statistics for a second. 20x increase in demand. These are existing large markets, and there are huge operations already in place. The idea that we need to create new technologies in order to meet future demand instead of just scaling up the operations we already have is really sort of a remarkable one. And I think the scale is such that we will inevitably have many solutions succeed. We need to. So we're expecting this mosaic future in which a lot of different technologies are at play, and they all have different pros and cons, as you're saying. So talk about a few of them. You mentioned deep sea mining. This is very cool, where they have there's this microbial process, I believe, where some microbes sort of deposit rare earths. Not rare earths, well, sometimes rare earths, but like cobalt and nickel. They pull them out of the water and deposit them into these nuggets that sort of sit on the ocean floor. And there are these companies that are deploying these robots that drive down to 10,000, 5,000 feet, 10,000 feet and pull out these like cobalt rich nuggets and pull them to the top. An amazing solution. A couple people say that there's like a little bit of risk about what happens to disturbing this, honestly, in my opinion, pretty lifeless part of the world. But it's an interesting question. But that will probably be a big part of our solution. There's a ton of new ways to pull lithium out of these sort of unconventional resources. Lithium normally, historically, comes from these really high-grade brines in Chile and the so-called lithium triangle, where the lithium brine quality is so high that you can effectively dump the brine into a big empty plane and just let it evaporate over 2 years. And then what you're left with is an almost pure lithium salt, a little simplified, but not much. Those are incredible resources, but there's not nearly enough to meet our demand. The other half comes from hard rock mining in like Australia and New Zealand, where they have these rocks that are like 15-20% lithium by mass, which is really high, really good quality, and just sort of melt them, crunch them up and melt them. But that's also, even those two scaling up are projected to be far short of what we need. So what we're looking for now are so-called direct lithium extraction technologies, where there's tons of other brines in the world, a lot of groundwaters, like the stuff that gushes out of geothermal wells, the Salton Sea, for example, if you've heard of the Salton Sea, that has like decent lithium, but not nearly good enough. It would be super expensive to pull it out by doing one metal at a time. Like if we purified the sodium out, purified the magnesium, this would be very expensive. So what we're developing are technologies where we can take huge amounts of water with low lithium concentrations and pull the lithium out directly. There's a lot of chemical approaches that are looking very good, although there's a lot of folks in the DLE space. And thinking about this mosaic again, I think we can think about the different pros and cons of the different approaches. Some of those categories are domestic versus international production. For example, those two traditional methods, neither of them are domestic. And for a lot of reasons, the US wants a domestic supply stream. We can think about the quality of the resource that we're pulling out of, high grade versus low grade. A lot of these chemical approaches require 400 ppm lithium for them to work. And we're targeting these really low grade 20, 50 ppm, which is a measure of concentration. So yeah, there's a lot of approaches. We're going to need a lot of them to work. Happy to talk about any of them more if you want.
Yeah, no, I think I just wanted to go deeper on biomining and for you to explain a little bit with the process. So we looked at the diagram to understand a little bit of what's happening, but also like how do you partnership, right, with, I imagine, both oil and gas company, and maybe that's time to bring up that story about what happened in the bayou.
Yeah. So the sort of observation is that a lot of DLE approaches today are going after drilling new holes in the ground to access these relatively high-grade resources in the US. There are these spots in Arkansas where if you drill down deep enough, this 400 ppm lithium water will come out. It's amazing, and it's going to be a really important part of our solution. But the oil and gas industry is producing billions of barrels of water every year, and there's enough lithium in that supply or demand. The problem is threefold. First, it's a low concentration. Instead of 400, it's like 20. And that's just a lot of chemical approaches just sort of crap out right there. The second is contamination. This brine that's coming out of the oil and gas well is filled with oil and gas. Not filled, but it's abundant enough that it would gum up a lot of other operations. And the third, this is the one that we really sort of learned a lot in the field. These oil and gas sites are remote and they're spread out. So any individual field is unlikely to have, huge volumes. They're objectively large volumes. It's like, 10 Olympic swimming pools a day, for example. It's a lot of water, but it's not enough lithium to justify $1 billion facility. So we to go after oil and gas, we need solutions that can handle low concentration, contaminated, and relatively small outputs. And then we'll have just lots of them, lots of these facilities.
So what happens to that water just to get the full picture? Do they just release the water?
Yeah, it's funny. The water is so salty typically that there's nowhere you can put it without like killing, nowhere above ground. So what we do is we inject it back down. This is a different process than fracking. It often sounds like fracking. This is fracking. There's some debate over whether or not that jeopardizes the quality of like our, causes earthquakes effectively. This water disposal is pretty innocuous, and we just put it back where the oil came from. It can actually be a good thing because it stabilizes the pressure of the reservoir. But yeah, we pull up all this oil, gas, and water, and then we re-inject the water. Interesting fact: in the U.S., we pull out 10 times as much water as we pull out oil. So this water management is a very pressing question, and very much like front of mind for oil and gas operators.
Got it.
Yeah.
Yeah. So tell us more about maybe the relationship you have with these companies and how does that impact your go-to-market? Do you show up on the rig, and how do you build trust also as a startup?
Yeah. Luis and I in the early days had a lot of like cold calls to oil and gas operators, which was tough. You go on the website and you find like a contact number, and you just call and you're like, "Hi, I'm a synthetic biologist in the Bay Area working on like a strain," and they just totally uninterested if they pick up at all. So that is a very hard way in. The thing about the oil and gas industry, one thing that I've learned is one thing that we've learned: a lot of snake oil salespeople in this industry. A lot of folks are pitching just junk ideas. So the operators, especially, someone at a small family, a small operation, really need to they're immunized against new ideas or someone pitching them a magic solution. So that was really hard to get in. And what wound up working really well for us is we've had 2 advisors now who were operators or very close to operators in the energy space in the US. And we've gotten direct introductions with like friends and coworkers and collaborators of our advisors. And through that, we've gotten some cool experiences. We had this trip down to Louisiana where we got to go on field at a couple fields and meet these folks there's some folks who've been running oil and gas fields for generations, which is sort of just a wild, interesting little phenomenon that I didn't know that these were family operations. And saw just how sort of rugged these landscapes can be. That was another sort of surprise. You drive down a dirt road for like 30 minutes and you're just like cars bumping all around. You're like, how the heck did they bring out like mountainous machines into this space and then drill a hole 2 miles deep? Like, how did they pull this off? But this is like actually an asymmetric advantage that the US has, is we're very good at drilling holes in the ground. Our oil and gas operations are really phenomenal technologically.
So it's still very fragmented from what I understand, right? You have to talk to a lot of smaller family-owned rig manager. How does that work?
Yeah. I think oil and gas is probably one of these sort of power law distributed spaces where there's some operator, you've like an Exxon or a Chevron that's moving, double-digit percentages of all the oil in the United States. And then you have all the way down to operators where they have one well that's been operating for the last 75 years that's producing, a barrel a day or something like that. And so, maybe we sort of started by talking to these smaller operators who were really amenable to conversations, and we've been sort of moving up into these more promising industrial partners. So we've gotten to have some talks with some of these really big water movers in the Permian and the Bakken regions. Are 2 spots in the U.S. that have a lot of lithium. And so we're now talking to the folks who run pilot operations for new technologies. We got past the filter. We're now talking to the people who are actually interested in new tech. And yeah, we're trying to move forward into a pilot. We're trying to do a pilot in 2026. We want to actually get microbes growing on fields starting next year is our goal.
Oh.
So yeah.
Okay, I think it's time for you to break down a little bit in simple terms. What does it mean to genetically engineer microbes and how does it work? What are the constraints? What did you find out during that process?
Yeah. Okay, right. So we've all these little oil and gas fields. What we need in order to pull the lithium out at those sort places is the ability to grow a microbe cheaply that can pull the lithium out. So how are we doing that? We have these strains of yeast. All microbes, incidentally, are little, it's like, how do we visualize this? They're little vessels. They're kind of like a submarine, right? And like a submarine, they would dunk them into water and they're kind of leaky. Water, salt, everything sort of gradually leaks in a little bit. And evolutionarily, the way the microbes solve this is they're studded with pumps. These pumps are little proteins. They're encoded in the genome. And the interesting thing, and very unlike a submarine, is these pumps are atom specific. So there's a pump that just moves sodium. There's a pump that just moves iron, more or less. So effectively, what we are doing, our engineering, is we're taking the pump that just moves lithium and we're flipping it. So instead of pumping lithium out, it pumps lithium. And once you do that, more or less, you have a strain of yeast that when you dunk it in this nasty brine, keeps everything else out, but pulls lithium in. It becomes very concentrated for lithium on the inside. And this is really a platform technology. You can swap out instead of swapping the lithium pump, you can swap a cobalt pump or a magnesium pump, for example. And simplifying a little bit here, but fundamentally, that's the biology at play. And this type of engineering, this type of protein engineering, has become a very exciting space in the biology world in the last few years with the advent of AI, right? So if you've heard of AlphaFold, if you've heard of ESM, incidentally, ESM, founded by my former boss at Loon, Sal Candido, at the Evolutionary Scale Company. So there are these AI tools that help us answer questions that we have about proteins very quickly. We can evolve proteins very fast in the lab, but with the use of AI, which we could talk about more. But the AI is really sort of a fundamental enabler for this type of engineering. Swap a pump around, it's kind of tricky, and the AI can accelerate it a lot.
Yeah, if there's more to say, it's interesting because in our previous talk 2 weeks ago, we talked about how AI and simulation helps create EV cars without having to build them because you're in a virtual world. I'm trying to understand if it's the same and you can do a lot just virtually with AI before you get in the lab, or what's the relationship between the bench and the protein mapping and AI platform?
Yeah, that's awesome. Right, and a great comparison. Biology is so funny. We really can't simulate it very well. It's like sort of this wildly difficult problem. But there's a few things we can do well. One is we can take a protein sequence, the thing that comes right out of the DNA, and we can predict its structure. So that's really useful, and that's a helpful starting point. If you know the structure of a protein, you can sort of stare at it and try to guess how it works. But the way we're using it more, and the way that's really, really, really important to us, is for what we call directed evolution. This is an idea that won the Nobel Prize by Francis Arnold a few years ago. And fundamentally, what we're trying to do is we have a protein that does something, and we want it to do something else or do something better. And what Francis Arnold did was, okay, we're going to take a protein, we're going to mutate it, and we're going to put it under selection. We're gonna make 1 million variants. We're gonna find the best one. We're gonna make 1 million variants of that. We're gonna find the best one. It's incredible that they were able to get this to work and make some amazing proteins. However, for us, screening 1 million variants of a protein is very, very hard. It's totally impossible. We can screen dozens of strains, not millions. So this was a famously problematic area in directed evolution. It really only works for proteins where they're amenable to screening millions of candidates. With AI, we can take 10, 15, 20 measurements of 20 variants of a protein, and we can project. We can learn from that very, very efficiently. There are these, you can look at, this is called low-end directed evolution. If you want to look at some papers, they're very exciting. There's this tool called Evolve Pro that sort of is kind of emblematic of the type of process that we're using. But we take these 15 proteins for AI people, we effectively embed them, we fit like a linear model or some regressor on top of the embedding space to have a predictor of sequence to activity relationship. But yeah, so this AI enables us to do evolution with just dozens of samples, which is sort of a wild idea. Evolution, which of course historically takes millions of years and millions of lives.
Do you bring water samples from the field to the lab, or do you also move the lab to the field? As you mentioned, it's very local, but also very spread out. What's the process?
Yeah, it's a great question. And actually, it was sort of stymied the directed evolution, or excuse me, direct lithium extraction field. People, it's very tempting to use just simulated brines. It's like, we've done an analysis. We know the composition of the brine that Chevron has at this field. We're going to make our own. We're going to add the salt and the sodium, the chloride, and the potassium. But what we found is that as a field, there's really no substitute for actual environmental samples. So 100%, we are for potential partners. We ask them to ship us samples, and we try our process. We dunk our microbes in their actual brine and see how well they perform. There's really no substitute for the real thing. But like you're saying, no substitute for the real thing. A lab sample is a sample that's been sitting in a bottle for 3 weeks is only so representative of the actual environment. So that's why we're pushing hard for a pilot facility. And these types of like new technologies, the pilot is a really important stage. No matter how good things look in lab, you have to put it into the field at a small scale to see that the process works live. So that's what we're aiming for in 2026. We're building like a shipping container-esque model of the process. It's not that big. We're thinking like a tube that's 10 liters. It's like I don't know, like the size of a pair of skis or something like that. It's a small scale, but big enough that we can like run it live and see how well it works.
I actually had a question about capital. Obviously, when we talk about climate solution, many of them are very physical, so probably higher cost. What's been your approach to fundraising, capital raising, or even investment for AlkaLi Labs?
Yeah, it's really hard. There's this valley of death that folks talk about where you can have a technology that looks really, really good. And yet, in order to show that it works at scale, you need to fund a pilot. We are really focused. In the long term, we want to be one of the lower capital requirement DLE technologies. There's a lot of technologies that don't work until you have a $2 billion facility, and we find that really intimidating. So we're aiming to be just lower cost, a $20 million, $30 million facility. And that's in the long term. In the short term, we're looking down this pilot facility production, building out this pilot. And just like other technologies, we are aiming for a combination of non-dilutive grant funding from the government and dilutive funding from VCs. Venture capital is not meant for building facilities. We've been told this. It's sort of starting to sink in. Really, there are other funding mechanisms. There's project financing when you're far enough along, but for the pilot, you're really looking at non-dilutive funding and a small amount of venture capital. And we are also in a good spot because we have capital-rich partners. So once we're far enough along, working with our partners to fund the construction of facilities is in scope, and hopefully something that we can start to flesh out with these partners as we get closer to them. How can we work together to fund a new facility that could be very profitable?
Yeah, I feel like a very symbiotic relationship with these partners anyway, and that
Yeah, it totally is.
looking for capital themselves. But I think it's interesting. How do you think about the current regulatory landscape and potential changes in policies? Is it something you anticipate, or just waiting to see what happens?
Okay, the biggest one, we don't know what's going to happen to climate funding. For the last few months, I think it's been a real question mark. And I think it remains one. So what that is to say, a lot of climate tech operations are super reliant on non-dilutive funding. Look at, gosh, like carbon credits. We don't know that all of a sudden our plans around carbon are sort of jeopardized. And for us, this non-dilutive funding for a pilot, non-dilutive funding for demonstrating our technology at scale, grants to help us develop our technology, all a little less clear what the future of that is. However, there's hope. Domestic supply of critical minerals is still a really important mission for previous administration and for this one. And that's something that we're working on. We want to be able to supply the U.S.'s lithium from U.S. resources. So their funding may still exist. And the other regulatory angle, actually also around domestic, there's this interesting terms that were written into the bipartisan infrastructure law, where there are subsidies for electric vehicles from the government. And there's this cool clause in there that says the subsidy goes up if the vehicle is made of more domestically provided minerals. And there's these, I was really impressed. There are these cool terms where the threshold for domestic supply keeps going up year after year. It's a really cool way to drive investments in domestic production. And the way people expect that to look is we'll eventually wind up with a bifurcated market where there's one price for international lithium and one price for domestic. So if we're providing domestically, we get a little boon. And that just is really sort of an inevitability of this regulatory choice to subsidize electric vehicles made with domestic minerals.
Yeah, I think the domestic agenda is getting very clear. I see that also in biomanufacturing, more incentives to build manufacturing capabilities, just to be less dependent. And then if you start adding tariffs on top of that, I think there's a very clear strategy and opportunities for sure. Plus oil and gas is not going anywhere. I wanted to ask with your technology, so we're talking cobalt and lithium today, but can you imagine scaling it to any other mineral? Or is it completely different path and different approach?
Yeah, totally always talking about other minerals. Lithium and cobalt, so important for EVs, high value per ton. That's sort of a requirement for this technology to work. A little extra color on the technology. Strictly speaking, a cell is more than just a uniform vessel. We're working with yeast, and they have this extra compartment inside that's used for storing metal. And we're actually storing our metal inside that compartment. And you can kind of shovel any metal you want in there. Nature has these repertoires of pumps for different metals that have been developed over millions of years, and we can just sort of mix and match our favorites with a little evolution mixed in to make them work better. But yeah, so there's rare earth elements are a really interesting one. Cobalt, lithium, nickel. And those are the ones that sort of jump out. Even magnesium, these microbes actually are natively very, very good at pulling out magnesium. It's a lower value per ton, so that gets a little tougher. But yeah, the technology is pretty robust. There's even applications in people have looked a lot at bioremediation. We were talking to someone, speaking of the USAID office, which is no longer, who was trying to fund the removal of lead from drinking water in India. And that's something that an engineered microbe could do pretty well. So we're sort of talking about those as well. But yeah, lithium and cobalt are our main line for now.
Can you help me like imagine how do you harvest it back, right? I understand the yeast is capturing the lithium, but how do you harvest this? What does it look like?
Yeah, it's a great question. We sort of glossed over that diagram earlier. It's like we
Yeah.
mix the microbes in the brine and then we separate it. What does that look like? It's actually right. So in the process engineering world, that process is called dewatering, where you have like some solid stuff floating around in liquid, and you want to get the water out of the solid stuff effectively. And there's a lot of technologies or a lot of processes for that. They're the simplest one that's often used in municipal water treatment is oh, Luis always remembers the name for this, and I always forget. It's like a settling tank. You have this broad sort of pond. You pump your water in, and it's relatively thin, so the microbes just settle over time. They're heavier than the water. They land on the ground, and you have like this vacuum that sucks it all up. So that's one stage of dewatering. Another is centrifugation. So there are these very cool like school bus size centrifuges that have a like a 30-foot long barrel that spins along a horizontal axis very, very fast and separates the heavy microbes from the slightly less heavy water. These processes are massive and employed at large scale in municipal water treatment and oil and gas already. So we can just sort of leverage all this existing equipment.
I think it's fascinating because we are mixing like the cutting edge AI, putting folding with things that have been here for years and years and are just come on, I guess, and easy to
Yeah.
access. So that's
Yeah,
awesome.
there's this funny vision of like a bioreactor, which I think most places today, this is something that you have in like a sterile facility where people are like walking up to it in white coats and nice gloves. And now we want to put that into the middle of a barren field in Midland, Texas, where it's like exposed to the rain and the elements. They'll put it in a little shed or something like that. But we're really putting these this like cutting edge biology like out there in the field where it can actually be doing some good.
So you talked a little bit. Oh, no, I just wanted to go deeper because it's exactly what I'm thinking. Like you're coming from Silicon Valley, very innovative. You're talking to people who've been doing it as a family for years. Is there any other learning about how to really talk the marketing, the positioning, the messaging? We always like to understand a little bit some of the secret sauce of founders who are doing amazing things, but targeting very traditional environments. So what's been your learning and did you find something that works really well?
Yeah. Oh, I will say I have been surprised and delighted that the folks we talk to are super excited about having this other business model be part of their operations. Like they want to provide provide the world's minerals, and they think they have the skills and the opportunity to work on that. So people have been super amenable to this sort of shift. And talking about the exciting science and the AI as persistent protein engineering doesn't get us very far, has been
Okay.
sort of our finding. I think we talk about we had to do our homework. We use industry specific language. We don't talk in liters anymore. We talk in barrels. We talk about a process in the terms of any other process that can happen on the oil and gas field. The fact that it's happening through AI designed microbes is an implementation detail. That's fundamentally been it. We want to be another service provider in that large ecosystem. We just happen to be new.
I love that. Language market fit, right? Finding the language that your audience is speaking and refining it.
And these advisors have been helpful. We had people have really like we show them our deck and they're like, oh no, like you sound like a fool when you say it's not brine, it's produced water. It's not, don't talk in liters. No one knows liters, talk in barrels.
Interesting.
Very important to learn that language.
Yep. So it's been your strategy was really your advisors. What about building the team? Where are you investing right now? Is it more scientists? Is it more BD, manufacturing experts?
Yeah, we're still small. We're hoping to go into a seed round very soon. We have a scientist, and he's incredible. He's a he's a workhorse. We uh, did sort of the googly thing, or something you learn at Google, of you go in with a very clear rubric for what you're going for. You design the qualifications that you need ahead of time, and then hire precisely based on the rubric. It's a really important way, I think, to avoid these sort of hiring biases that can come out if you just chat and see whether or not you like each other, right? It's very easy to wind up, you just vibe with some people, often who are more like you, you know, and that's not appropriate. That's not how you find the best people. You find the best people by writing out your rubric and hiring to that. So yeah, we looked for someone who could help us with these big technological pushes that we're going after, and hired him. And the fact that he winds up being like really fun to work with was just sort of a lucky benefit, I think. I think that was our approach. It was like scientist first, and then we got lucky that he's like awesome as a person.
That's really cool. So I know we're almost at time. I just want to make sure I can ask a few questions about the community. So first, we love your vision. Where do you think you're going to be in 5 years? Or if you have a magic wand, where are you in 5 years?
Yeah, yeah, 5 years. Wow, feels so far in startup time. So we're hoping to get a pilot facility out into the real world in 1 year. And starting about a year from now. So 2, 3 years from now, we've shown the technology works in the field. 5 years from now, we're hopefully building our full scale facility, our first of a kind full scale facility, with a partner that has good lithium, and we're really like excited to deploy with. So 5 years, I'll hopefully be taking a lot of flights out to somewhere in the U.S. that has a budding construction site for an alkali extraction facility, or actually 5 years finished construction site, I think. Yeah.
Very cool. Probably more Louisiana or Texas
Or North Dakota. There's some awesome resources in North Dakota. I hear it's stunning up there. I'd really love to go and make
good
it that
to know.
opportunity.
Okay, well, we're taking notes. Last two questions for people who haven't made the jump yet to climate tech. What would be your advice?
I'd say specialize. And that worked for me, at least. Like I feel like I learned about biology as like that was sort of my specialization. I think that every specialty under the sun is important for climate transition. And having a specialty is really helps to get in the door at these startups. It doesn't need to be a lot. Go to a conference. Pay out of pocket to go to something that you think is interesting in the oil and gas produced water, or solar panel manufacturing, or I bet there's a conference where like PG&E goes, or they talk about utilities. Just go, pay it, take a couple days off and learn a little bit. I think that having like a little bit of a specialty to start with is a real foot in the door when you go to actually interview with startups. Helps you learn the language of the space,
Yeah.
and I think that goes far toward getting into a new space. And I think someone else said this on a previous someone else you spoke to, but just go for it. You don't need to wait that long. Everyone here is doing an amazing job, and I'm sure I think everyone here has a good pedigree and will do well in interviews, and just hop it, you try it out, and go to the conference. I think the conferences are so interesting. Go to like something really technical and just take notes. Your brain will figure it out, and you'll start talking the talk real quick.
And last question, how can this community help you beyond having grandparents in North Dakota and with the whole oil field?
um well, I think you and a lot of other folks, I'm really excited to keep like talking to Zooglers and climate. I think a lot of people with sharp eyes sort of on the ecosystem and the space, this funding thing, for example, we're really going to have to all figure that out together. I think there's going to be approaches that we will learn as a community, and I'm really excited to talk to folks at happy hours about the clever ideas that people have had for how to fund a pilot facility when grants seem a little less viable maybe than they have before. So I'm really excited for the community activities. We may also be hiring in business development soon, so we may be reaching out to some group channels.
Hope it was helpful. I learned so much. Thank you, Jacob. It's a masterclass. Thank you, everyone. I think it's time for us to wrap. It was so good to have all of you today. We'll share the recording and some of the resources, and please don't hesitate to reach out to me or to Jacob directly if you have follow-up questions. And with that, have a great week, everyone.
Thank you.
Take care.
Thank you.
Thank you. Bye.